Okay, this is now the second part of 7.3, part B. And the last one we did was derivatives. We're still going to do derivatives, but we're going to deal with integrals. So in order to do number 23, what we need to do is recall the fundamental theorem of calculus. Remember that if you have an antiderivative of the integral from a to x as f of t dt, if you want to differentiate this whole thing with respect to x, all you do is just take the integrand and replace the f of t by where that's the limit of integration, upper limit, it becomes f of x. Okay, so really it's just undoing what you're integrating, you get back the original function. Okay, so another thing we have to remember is that if you have e to the natural log of x, it's like this whole thing collapses because they're inverse operations of each other, so you get back the x right there. Okay, let's look at number 23. Number 23, you have y equals the integral from 0 to the natural log of x, sine of e to the t dt. Now remember, this is if you have the fundamental theorem of calculus also applies if the upper limit is a function of x. All you do is just apply the chain rule. So in other words, for this particular case, okay, let me just, in addition to that, okay, so also if we want to differentiate with respect to x, say from a to u of x, all right, of f of t dt, this is just f of u, and then you divide and you multiply by the derivative of u with respect to x. You multiply that. So it's really just an application of chain rule. So that's what we're going to use in this particular case. So I think we're ready to take the derivative. So now y prime would be equal to, so just take out all the integral sign, and it's going to be sine of e to whatever is the argument that sits here. You replace it by the natural log of x, and then you don't stop there because you multiply by the derivative of the natural log of x by chain rule. All right, so that's equal to, the nice thing is that this collapses into x, so it's just sine of x. And then what's the derivative of natural log of x? 1 over x. So the final answer would be sine of x all over x. There you go. All right, let's keep going. What about the next problem? Okay, here in number 24, we're asked to look for y prime, okay, but you see that we have two limits of this integration. What we need to do to be able to apply the fundamental theorem of calculus, we got to split this up into two integrals. So it's now, we break it up into, okay, we take the same, so it's e to the 4 root of x up to a of the integral from the natural log of t dt plus, you see how you continue on. This means that a sits between these two limits of the integration. So a to e to the 2x natural log of t dt. And then in order to apply a fundamental theorem of calculus, this has to be up here. So to do that, you just reverse the limits of integration. Then you put a minus right there. Okay, so it's now, oh, okay, we need to put an a here. So now it's the negative of the integral from a up to e to the 4 root of x natural log of t dt plus a up to e to the 2 of x integral from a to e to the 2x of natural log of t dt. And I think from here we're ready, because now we're ready to apply the fundamental theorem of calculus. We can now say that y prime is equal to, all right, how do we do that? Okay, so remember, you just drop the integral sign, evaluate natural log of t at the upper limit. So it's going to become the natural log of, instead of t, we apply e to the 4 root of x. Then we don't stop there, because now we take the derivative of e to the root of 4 root of x, okay, with respect to x. All right, then plus, same thing here, it's going to be, if we differentiate this, it's going to be the natural log of, what's the argument? E to the 2x times, chain rule, the derivative with respect to x of e to the 2x. So the rest is just simplifying. So let's see, what do we have? Okay, remember that the natural log of e to anything, so another note to remember. Just so, the natural log of e to the u is u. Okay, so that whole thing collapses because, again, natural log and e are inverse operations of each other. So this becomes minus 4 root of x, and then you multiply by the derivative, so e to the 4 root of x. Again, chain rule because that's not yet the derivative of the whole thing. So now multiply by 4 times 1 over 2 root of x, because that's the derivative of root of x. Okay, and then plus, let's see what's happening here. So now this becomes 2x times e to the 2x times, not done yet, keep differentiating by chain rule, the derivative of 2x is 2. So what would be the final answer here? So that cancels out, and then that cancels out. We're left with a 2. So the final answer is going to be, let's see, it's going to be minus 8, all right, because there's 2 and 4, 8 e to the 4 root x, okay, and then plus 4 e to the 2x, and that takes care of your derivative. Okay, so let's keep going. Okay, now since we've finished all the derivatives, it's time to evaluate integrals. Now recall what the integral or antiderivative e to the u du, it's just e to the u plus the constant. So our goal in the next few problems is to find u's and du's so that we can apply this definition of the integral of e to the u du. So let's look at number 29. In number 29 you have a sum of two terms, different exponents of e. So really you have two expressions of e's. So what I'll do, I'll split this up. So it's going to be the integral of e to the 3x dx, right? So it's just distributing the integral sign, okay, plus the integral of, I'll put the 5 out here since it's just a constant, e to the minus x dx, all right? Okay, and then I'm going to take the integral first of the first term. So let u equal to 3x. That's the only possible way that we can get an e to the u, is to let u be 3x, so that this becomes 3 dx. So to match up with this, we need to divide everything by 3, so that gives us 1/3 du. Okay, so now you back substitute that. This is now 1/3, okay. I just put the 1/3 and then du, integral of e to the u, okay. So that's just pulling out the 1/3. Remember your dx is 1/3 du, so I just pulled it out. Right, so this becomes 1/3 e to the u, okay. So it becomes 1/3 e to the 3x. Right, now we're almost there. Let's take a look at the second part. All right, so let u equal to minus x. So what is your du? It's going to be minus dx. Okay, so your dx is really just minus du, so that we can have a match right there. Okay, so how does this look like then? So this becomes plus, right? So we have 5, the integral of e to the u, and then minus du, right? Okay, so now I'm going to pull out that negative. So we have here plus a negative 5 e to the u. So minus 5 e to the minus x, and then finally plus a constant. Okay, and it's the nice thing about integrals is that we are able to verify whether we have the right antiderivative by differentiating. So let's try and do that. What is the derivative of e to the 3x times 1/3? It's going to be e to the 3x times 3 cancels out the 1/3. So there you go. That's a check. Okay, and then what's the derivative of minus 5 e to the minus x? It's going to be minus 5 times e to the minus x times -1, because that's the derivative of minus x. And so negative times negative becomes positive. So see, that took care of the plus, and you get the same integrand. And that did check out that the antiderivative or the integral of number 29 is this one. Okay, let's keep going. Right, here are this is very simple, but I just like to show you how cool it is that we have these limits of integration. So what is the integral of e to the u du, or e to the x dx? It's just e to the x. So this is now equal to e to the x. But then what are the limits of integration? It's going to be natural log of 2 and natural log of 3. So that's equal to e to the natural log of 3 minus e natural log of 2. And the nice thing is that this collapses, so it's just 3 minus 2, which is equal to 1. So I like it again that we ended up with a 1, because it's just this whole thing, this whole integral sets to be equal to 1. It's like infinitely many ways of finding what 1 is equal to. All right, now in 33, it's just slightly different, but what we got here is that we let u, what do you think is u? Well, our dx is just dx, so that's a possible du then, which means our u has to be x plus 1, so that du becomes dx. And do we have a match? Yes. So now there's our e to the u, and there's our du. So this is, and now I'm going to pull out the 8, so it's going to be the integral of 8 times the integral of e to the u du. So writing it back, it becomes 8 e to the x plus 1 plus a constant. Again, that's that is easily verified. When we differentiate this, we just get e to the x plus 1 times 8 times the derivative of x plus 1, which is just 1 sitting right there. Okay, so, and of course that's 0. So that checks out. So we did get the integral of number 33. Oh, now, what about number 39? Let's see what's number 39. Well, in number 39, we just, what I did here is rearrange a few terms so that it becomes obvious what's going to be your e to the u. Okay, so let me rearrange and put these together. And so I wrote it as the integral of e to the t squared times what? 2t dt. See that? And obviously, you know where I'm getting at. So this is going to be, let u be what? U is now minus t squared, so that du equals minus 2t dt. All right, so you see now we have a match, because 2t dt, 2t dt is equal to minus du. So now everything can be written up nicely as this is now equal to, I'll put the negative out here. So there's your negative, and then we have e to what? What is that? There's your u, and here's your 2t dt is your negative du. There's that negative in the front. So we have a minus e to the minus t squared plus a constant. Again, to verify whether this is the correct antiderivative integral, all we have to do is just differentiate. So what's the derivative of e to the minus t squared? It's just e to the minus t squared multiplied by the derivative of minus t squared, which is minus 2t, and you see there's that part. Okay, so minus of a minus 2t, you get positive 2t. There's your check, and it works out. All right, okay, let's keep going. Wow, what is this? It's got secant squared theta d theta. What do you think? Well, obviously this looks like a derivative of something. So what is that something? That turns out to be your u. So first of all, what we need to do is break this into two integrals. Okay, so it's now from 0 to pi over 4 of, I'm going to distribute that right here. So it's going to be secant squared theta d theta. Okay, all right, plus, split this up, from 0 to pi over 4 of e to the tangent theta, secant squared theta d theta. Okay, so now we're splitting this and integrating it one at a time. So this is really simple because you know that that's the derivative of tangent. So the first part is equal to, I'm going to write that here. So it's equal to the tangent of theta, right? Because that's the integral of secant squared theta d theta, evaluated from 0 to pi over 4. And once you simplify that, that's just equal to the tangent of pi over 4 minus tangent of 0. So that gives us 1 minus 0. So that's equal to 1. So far, we've gotten that this is equal to 1. Now, let's move on to the next one. Right, so here, what would be a good guess? We need to do a substitution. Use the substitution method. Let u equal to, that's right, tangent of theta. Why? Because we know that du is equal to secant squared theta d theta. And there we go. We have a match. This becomes the integral of e to the u du. So that becomes e to the tangent theta. All right. And then it's evaluated from 0 to pi over 4. And if we do that, we're going to get e to the tangent. Remember, what's the tangent of pi over 4? We know that it's 1. So e to the 1 minus e to the, what's the tangent of 0? It's 0. So e to the 0. So this is e minus 1. So if we add everything together, what we'll have will now be, okay, add up all of that. So this and this part, combining them, is equal to 1 plus e minus 1. So cancel out each other at once. And now our final answer is just e.